yes, on behalf of the Spectrum Scale user group, welcome to Spectrum Scale Expert Talks. I'm Bill Anderson, and I'll be your host for this session. This next talk is on Data Accelerator for AI and Analytics. Yes, Spectrum Scale user group hosts a number of digital events throughout the year. You can view past recordings of events using those URLs there on the slide. You can also join us. We're a community of folks trying to help each other use Spectrum Scale. Yes, we're independent. We are not IBM employees. We work with IBM to develop events. We're not a replacement, for opening a bug report or that kind of thing. Rather, we're an informal community. And yeah, we'd love to have you join us. There's the URL. And there are 5 main folks who organize these events, and there's a list of us. And you can access past talks, again, like I mentioned, using the URL there. We've had a number of talks over the past months. And also, just a reminder, there will be another session on Wednesday, November 18th, that where we'll cover what's new in Spectrum Scale 5.1. Also, we'll have a panel of experts where you can ask any questions you want about Spectrum Scale. And yes, so for our next talk on Data Accelerator for AI and Analytics, our speakers are Simon Lawrence and Gero Schmidt.
Yeah, thanks a lot, Bill. My name is Simon Lawrence, and with me is Gero Schmidt. We both work in the Spectrum Scale development team in the area of big data and analytics. And in the following, I will talk about the topic of Data Accelerator for AI and Analytics, or in short, DAAA. And Gero will help with any questions that you can bring up in the Q&A chat. A short outline of this session. It's about customer demands and requirements received in the area of big data and analytics and what we have learned from the market on what is needed. I then will briefly discuss the built-in caching functionality of Scale and how we use it to provide a high-performance tier named HPT. HPT is also the basis for a solution that we call Data Accelerator for AI and Analytics. And this is followed by a 25-minute demonstration of the DAAA solution using an autonomous vehicle workload as an example. Following some questions that got raised on this topic, I have a lot of data. Which one do I need for my analysis and where is it stored? Or I have received a lot of new data. Some of it's gigabytes, or in many cases terabytes and more of size daily. How can I automatically include the new data in my analyze process? Or now I have those fast GPUs, but my storage is too slow to feed the GPUs fast enough. Or even I have high performance storage, how do I make sure that I don't reach my capacity limits? Or another question, how can I let several data scientists work with the system at the same time? How can I ensure that my analyzed data is always up to date? And another question that often was brought up is how can I easily and efficiently install and run my containerized workloads? And we have summarized the whole as a theme here. We want to simplify the work of a data scientist and a storage admin. A data scientist should be able to easily find and use the data he needs for his analysis without having knowledge about the underlying storage systems and architectures. And now, of course, you can simply move the work to the storage admin, but we also want to ease his daily work. So all of this should help to get to results more quickly. So how does it often look like in practice today? The data stores are getting bigger and bigger. So far, there has been data tiering, which was mostly based on the number of data accesses, means if data is hot or cold. In the meantime, due to the amount of data, not every as hot declared data can be kept in fast and high available storage. Further, parts of the even declared cold data are needed for analysis. We also see that more and more workloads are moved into containers. And for the ever faster GPUs, correspondingly faster storage is required, which can supply the GPUs with data fast enough so that they don't idle. In order to be able to offer a solution for this, we took a closer look at the entire workflow. And you might have seen this picture before, showing the enterprise data pipeline. First, there is an ingest phase in which data is loaded into the system. This can be an object store or high-performance storage. Then the data is usually first classified and cataloged, and then to be analyzed in the next phase. And I have summarized this picture a bit and put it from bottom to top instead of left to right. So we have a capacity tier or data lake in which very large amounts of data can be stored. Goal here is to minimize the cost of storage. $ per terabyte is the key. The storage is highly available and reliable. The data usually is stored here for a very long time. Then we have the high performance tier. The fast GPUs or other accelerators run here. This is where IOPS and low latency with random I/O come into play. This storage is rather small compared to the capacity storage, and usually lower availability is requested here. Now the question comes up, how do we get the data from the capacity tier into the high performance tier? Metadata search engines help us to find the right data, and workload and process managers ensure that the data is loaded at the right time and system loads are properly distributed. If we look at it closer, the high performance tier is more like a cache, and the capacity tier acts like the home of the data. And if you worked with Scale before, cache and home probably remind you of the active file management functionality, AFM, that is already available and built into Spectrum Scale. AFM ensures that data from a home site can be loaded into a cache as quickly as possible and remains there in sync with the home site. And we are now building on this AFM functionality. Object storage is being used increasingly as capacity storage, either on-prem or in the cloud. However, it was not possible to connect AFM to an object storage. That is why we have been working on an object store extension, and it is now available with the Just G8 Spectrum Scale 5.1 release. First for the S3 protocol, but additional will follow. Anyone who has already worked with object storage recognizes that actually a file world and an object world come together here. Connecting those is particularly difficult when it comes to data security and metadata. AFM functionality helps us to connect the capacity and the high performance tier. Now we add some high performing storage, such as an ESS 3000. And now here you see the technology that we call high performance tier, or HPT for short. To meet the requirements outlined at the beginning, more is needed. In many cases, a separate compute cluster is generated as shown here. Then we also need a workload or process manager that takes care of the whole process and the utilization of the system. And a metadata search engine helps to catalog and to find the right data. And this is what we call overall a solution data accelerator for AI and analytics, short DAAA. I also mentioned containerized workloads earlier. Therefore, we integrated with Kubernetes and also OpenShift. The Scale Container Storage Interface driver, CSI, is used to access the remote mounted data. If we now come back briefly to the questions asked at the beginning, I have marked the answers in the DAAA solution picture. So how can I catalog my data and easily find it again? Or how can I automate the analysis process when loading new data? The integrated metadata search engine and the connection to our object store or another storage system like an ESS 5000, any Scale cluster or an NFS storage system help. How can I ensure that my high performance storage does not overflow? What helps me to run several data scientist jobs in parallel? That's a workload manager in connection with AFM. AFM also helps to ensure that the data in our high performance tier is in sync with the capacity tier. And when it comes to running containerized workloads simply and efficiently, the Kubernetes and OpenShift integration helps. So summarized, with the Data Accelerator for AI and Analytics solution, we are able to bring the right data closer to our AI applications at the right time. We are able to get to results faster without generating a real independent copy of the data. And DAAA can be easily integrated with workload managers and metadata search engines. As an example, Spectrum LSF and Spectrum Discover. We also want to keep an eye on end-to-end security and monitoring right from the start. So our goal or theme, simplify the daily work of data scientists and system administrators and use the storage systems more efficiently to get to faster results. But what would be a real-world use case for this? Mid of this year, we worked together with NVIDIA on a proof of concept in which we showed how deep neural network workloads could be scaled horizontally across node boundaries and being managed by OpenShift. If you're interested in the details, please have a look at the Redpaper or our Spectrum Scale expert talk number 8 as shown here. And I need to shortly give you some more details on the example so that you can see the value of the DAAA solution. Obviously, we needed a data set we could work with, and we used the Audi autonomous driving data set. It consists of images, labels, and data recorded by 6 cameras and 5 LiDAR units, providing full 360-degree coverage. It includes more than 40,000 frames with semantic segmentation images in 38 categories. The 2 pictures, or also called frames, are shown here as an example. The left shows the original recorded picture, and the right one shows the segmented frame, which provides us the master when looking at the amount of pixels per segmentation. It is common in industry that each training frame carries several hundred metadata tags. In our experiments, we relied on the A2D2 dataset without the help of other data sources. On uploading the dataset, the available information was extracted, such as the presence of certain classes and their pixel count. The right table shows an example 2302 pixels for pedestrians in a selected frame. If we now use this picture in our validation data set and compare the amount of pixels our model detected as pedestrians, we can detect how good or bad our training is. One of the most challenging engineering tasks is building the right training and validation data set. The validation of a trained neural network in a variety of situations will give confidence about its performance and weaknesses. As an example, the deep neural network we used in our test performed well on large objects, but did not do well on smaller ones given the object occurrence is balanced. This also happened with the randomly chosen subset of our training data set. We have evaluated a training after just 20,000 steps using a confusion matrix shown on the right. For a perfect predictor, the diagram would only have a line from the top left to the bottom right. That would read as the network would have classified all pixels of a certain class right. And here you can see 2 observations from our test. The first one is there are classes where the very bright ones on the line, such as the class number 1, which is a normal street, or the class number 9, which is the sky, or also class number 11, which is a nature object. Those can be detected very well. And when looking deeper at the metadata, we can see that the frequency of those pixels occurring correlate. In the example, the normal street appears 22%. In contrast, other classes such as roadblocks appear with only 0.85%, and the frequency of object occurrence is not sufficient. The second observation that you can see here is that the data used for the evaluation has no representatives for the bicycle class, which is 19 down here. Thus, the validation data set needs to be extended. Means we need to add frames into our data set that show bicycles. How can I easily find and use the right data to extend the data set? That is where Spectrum Discover gets into the picture. Discover is optimized to search billions of files and objects for its metadata in very short time. And in combination with Spectrum Scale AFM, we are able to provide the right data at the right time to the GPUs. To show you this in action, we would like to show you a short demo now and give you some details how it works. The first part will be about some details on the AFM functionality, followed by 3 use cases. The first one is that a data scientist uses the LSF Application Center UI to schedule an AI job. The second is that new data ingest starts the AI job. And the third is doing the steps like query discover, changing the caching the data, and so on to trigger this via a Jupyter notebook. So I took a short I recorded a short demo, which I will now also comment on. So first of all, some background on the AFM and its advantages. I divided this up here. I opened 2 PuTTY windows to show the functionality. The left window corresponds to our home site and the right window to our cache site. Let's look at the content of the bucket in the left side. What's in our S3 bucket? We see it's empty. What does our AFM file set look like that has the connection to our S3 bucket? We can see that with MMLS file set. So the file system in which our objects are cached in Scale is fs2_4, and the file set is named AFM this object. And the object fs parameter also shows that we are connected to an object store. If we take a look at what it's in there, it should actually be empty because it's connected to our bucket, which is empty, and that it is. Now let's write something in the bucket on the left side, just the current date. And I used the MinIO client copy command to load the file into the bucket. Let's see when that was. That was Friday, 10 o'clock 46 minutes. And with the MinIO cut command, we can look at the content of the file in the bucket. Content fits, so it worked. Now let's see how it looks on our cache side, the right one. Okay, the file is already there, and the content, let's look at that. Content is the same. Now let's go and write an update to the file on the cache side and check the content. The date now is Friday 10:47. What about our bucket on home side? MinIO cut on the object, and the time is right. So what actually did we do now? Let's get back to the graphics. We wrote an object in the object storage using the S3 protocol. We then read this object as a file in the cache storage and also updated it. And the update was synchronized with our object store automatically. So a very good extension to the AFM functionality by connecting an S3 object storage system. But why is AFM so helpful here, especially in the storage for AI environment? In simple terms, a simple copy back and forth would actually be sufficient. Well, there are a few great features of AFM that I now would like to show briefly. Suppose a data scientist knows most of the files he needs for his analysis. He can now have it cached by AFM into the high-performance storage. While the analytic jobs are running, it turns out that files are missing. Usually the job that might have already been running for a few days or weeks would break and stop. But if an AFM file set is hosting the data, this is not the case. For a file that has not yet been cached, but is requested to open, AFM in the background will cache this file from the home site into the cache and then delivers the now available requested data to the client piece by piece. This allows the job to continue running. So let's review this functionality also in our object example. Same picture as before, and we load some files into our object or in our bucket on the object store. Now let's see if we can see those files on the cache side. Here they are, but what is the disk usage at the moment? Let's look at that. It's 0 bytes. And that makes sense because we did not prefetch the data. A directory list request only requests and accesses the metadata. To prefetch the data, we create a file with the corresponding file names that are to be loaded. And I opened a new window to run a watch and see what happens to the file contents, means the disk usage of the files. Currently 0. Now we can start the prefetch with the AFM control prefetch command, the file set name that corresponds to our bucket and the file list. Let's go. Okay, prefetch was queued successfully, and we can see that the disk usage increases as the data also was cached. Now let's try to read the last 10 bytes of a file that is not yet in the cache. For example, the file 003 PNG. We can see that the 10 bytes are already there, and the rest of the file is loaded in the background if you look in the middle window. So that was maybe a bit fast. Let's do the same again for the 7.png file. Now we have the part we want, and still the rest is loaded. So great feature of AFM. So if we no longer need the data, we can delete it again. And I did this with the command AFM control evict, and again, the file list. My disk usage shows 0 again. So far for the AFM part. Now I'm coming to the 3 use cases mentioned earlier. The first use case is about the data scientist Dean simply selecting an autonomous driving template in the Spectrum LSF Application Center to start his analytic job. And I will show the full, complete automated process. Here's a brief description of how we set up and configured the entire solution and how it works. We use the IBM Cloud Object Storage as an object store. And for our demo, we run COS in multiple VMs. And I will shortly show how it is configured. So we have 5 devices configured, 1 manager device, 1 accessor device, 3 slice store devices, and we are working with 8 vaults or buckets. Following more details on the ones that we used. The first one is the A2D2 vault. It holds the autonomous driving data set, the data that is analyzed and gets cached to our GPUs. The second one is the AFM with object vault that you just already saw for the AFM demo. And the third one is the vault named models. So during our workload simulation, we will write data into the bucket to show also a write operation. We created a user, BDA, that is allowed to access the buckets. Further, we also configured the notification service. Whenever an object gets added or updated, an event is sent into a Kafka queue. Discover is listening on this queue with the consumer and will update its database accordingly. And as you can see, notifications is configured for our A2-D2 vault and also the models vault. That is for our cost configuration. We use Spectrum LSF as a workload manager, and in the first step, our data scientist team will use an autonomous vehicle job template that we built for him. And here's how we configured LSF. Jobs are triggered in LSF with certain user. For our case, we created the user team. Here on the dashboard, you can see the previously started jobs with their ID and name. It is also possible to create your own template for a job. And I did this for the autonomous vehicle use case, as it is shown here. So once it is created, Dean can simply select it up here. And the template for this job looks like the following. The user can add some details needed for the OpenShift environment, such as the persistent volume claim, or the namespace it should run in, or also the script that should be executed. Further, he's able to select the camera location the pictures should come from, and also some metadata details. An example, the frames should have a certain amount of pixels for pedestrians, for trucks, or whatever is needed. Then pressing submit will put the job into the queue, and it gets started when resources are available. So now what does the job actually do? I created a job chain that is started by the autonomous vehicle main job. This job creates 8 additional sub-jobs. First one will query discover about what data should be analyzed, and the just entered details are used for that. The second job recalls the data from tape if needed. The third job ensures the data is prefetched into the cache, and that could be data coming from an NFS server, from our COS environment. Also, we added a Spectrum archive system. The fourth job starts a pod in our OpenShift environment that does some sample work and writes data back in our models bucket. The fifth job ensures it knows the right location about the from tape recalled data and provides a to be evicted data list to AFM. The sixth job evicts the data as given by the file lists. And the seventh data is migrated back to tape. And the last job cleans up everything like log files and any temporary files. That's a configuration and setup used for LSF. As our metadata search engine, we use this Spectrum Discover. This is the second step, using the provided metadata to ask Discover for the right data and where it is. And we configured Discover as follows. The connected data sources are displayed on the dashboard here. The platform and the data source is shown. This is our models bucket in the IBM Cloud Object Storage. And the next 3 connections are the ones for our A2-D2 input data. First, the IBM Cloud Object Storage system. Second, the NFS server connection. And third, the Spectrum Scale archive connection. Discover also provides search capabilities directly in the UI. As an example, I searched for a certain frame, and here you can see the metadata details, such as some standards like the size, but also the provided autonomous vehicle details like car and bicycle pixels. I selected those in the column selection, and more are available also here. Those are the classes that I talked about earlier. So much for Discover. We used an ESS 3000 as our high performance storage. And here I have to mention that to use the AFM with COS functionality, Spectrum Scale 5.1 is needed. Our compute cluster is an OpenShift 4.5 cluster with 4 worker nodes. And the storage of the 2 scale systems is remote mounted. The OpenShift cluster also includes 3 master nodes. And the pod we are going to launch then accesses the data via the Scale Container Storage interface. The next step is that we use Spectrum Scale AFM to cache the data. And once this is done, we will start a pod to run some workloads, and we write data into our models bucket. And as the last step, we will clean everything up. So much for explaining our lab environment and how it works. Now let's get real and take a look at it. It wasn't easy to show the different processes at the same time, so I tried to divide the screen and briefly will explain now which window shows what. Here at the top left, we see a watch on the pod status that we will start. Currently, nothing is running in the namespace D. In the window below, we look at the pod's log and we'll see some progress messages when it is running. Further below, we can see details for the automatically provisioned persistent volumes. In the window on the right, as before, we run a disk usage on our cached file set to see how the data is prefetched. So now we only need the user interface for our data scientist Dean. And here we will start the job, and everything that comes afterwards is really fully automated. I didn't do anything in the background. The one job starts the complete workflow up to the cleanup. I also added some red boxes like the login one so that you can follow the action happening more easily. The workload and the pod will also generate data that we can see. It will show up in the middle window. So let's start. I did not want to pause, so if it goes too fast, we will see a second run. First, we open the autonomous vehicle job template. We enter details for the persistent volume claim, the namespace, and the script to run. And we want to get pictures from the front center camera. And they should include bicycles with at least 900 and maximum 1100 pixels. So now we press submit. And here we can see the AV job started and integrated the earlier mentioned subjobs. The query discover job already finished, means we already know which data we want to analyze and where it is stored. Data needs to be recalled from tape, that is happening now. Once it is done, data gets cached and the right window shows the disk usage. All data is prefetched. Now we provision the persistent volumes and the job is started. And as you can see in the lower left window, as a clustered parallel file system, Spectrum Scale also allows to share access to data not only across pods, but also across physical worker node boundaries in a read-write-many fashion. In the meantime, our sample workload is running, which is soon to finish, and we are writing a sample models file into our models file set. That just happened now. There it is. And our persistent volumes are terminating. Now we query discover again to get the latest details on localization. This could also be skipped or enhanced if, an example, the data is needed for further jobs. AFM now evicts the data to free up the space on the high performance storage, followed by migrating the relevant data back to tape, and last step was clean up the logs. And we also said we want to access the results with our object store. And as we have the AFM relationship between our file set and the models bucket, the data is present in the object store too. Running a min-IOLS on the models bucket shows it. So there's another use case that is very interesting, starting the AI job automatically after new data has been loaded. Also here, first a short explanation. As a first step, we will load more data into the capacity tier. A Kafka consumer listens to the new data, and the Discover catalog gets updated automatically. Once the loading finished, the AI job is automatically started again as step 2, and we will see the same process again. Step 3, Discover answers with a list of data that should be analyzed. Step 4, AFM caches the data into our high-performance storage. Step 5, we start the analytic job. And step 6, we clean up after work. So let's get back to our windows. Some get added now on the lower left. Here I start a small script that loads the new data. In the window in the middle, it shows a sample script that detects new data and waits for 1 minute until it triggers a new workload. And here I need to mention the following. The A2D2 dataset that we used has additional labels or metadata that get loaded in an extra step into the Discover catalog. This is a functionality that gets released with the next Spectrum Discover 2.0.4 release. And I loaded the data manually, but as this will not be the standard process, I skipped showing it. The window below will show some Kafka consumer and the events that got sent for each object that was loaded. So let's load some data into the object store. We can see the events showing up in the middle window, and the script detected that new data gets loaded. The script will wait another minute after the last event was received to detect that loading finished. The minute, of course, is just for the demo, probably is different in real-world scenarios. Some details on the automatically starting job while we are waiting. It will run with a slightly different Discover query. It will query pictures with a maximum of 1150 pixels for bicycles instead of 1100 in the beginning. I did this so that you can see that the cache data for the sample job really changes based on the Discover query results. So let's wait until the minute is done. Here we go. The script triggered the job, and in LSF we now see the job chain again. Discover search finished already. Next is data recall and caching the data. On the right you can see the disk usage again. The persistent volumes are provisioned now and the job will start. You might not have discovered the former values in the manual run about the amount of prefetched files, but if you did, you can see the amount of prefetched files and objects changed on the left window. Now doing some sample work. And finally write some sample output. There it is. Now again, query Discover. First terminating the job, then query Discover as the next step. Evicting the data as needed and migrate relevant data back to tape. So how about our models bucket? Also here we can see now two models as objects in our cloud object storage. And as a third use case, last one I shortly would like to show you. It is about triggering the different subjobs we saw from a Jupyter notebook. Also here I created a small sample. By running the code cells, it is possible to, in example, query Discover and create the file sets, recall data from tape depending on the Discover results, cache the data via Spectrum Scale AFM, and then also trigger any AI workload as needed. In real, this looks like the following. First, we create an object and read the configuration file. Next, we print the current status. We can also have a look at the configuration file. Here you can see that for this example, I said that with every command, also the new status will be printed. Then we can print the file list, which is currently empty. We didn't query discover yet. This one triggers a discover query with the given parameters, and it also creates the file lists. With this one, we can recall data from tape if needed. Or then cache the data into our high-performing storage. Run any sample workload. Followed by another discover query. Here you can see I changed the parameters that are given. We can evict the data and migrate the data back if needed. So as you can see, this provides very easy control about the full abstracted storage systems and architectures in our capacity tier. So that's all we wanted to show for the demo. Let's get back shortly to our slides. We also published an IBM Redpaper on this topic. It's available at redbooks.ibm.com. And we also provided an open source, the sample code that we used to make happen what you just saw. So you can go there and see how easy it is to get everything together and make it work. Yeah, I hope you found this session interesting. It brought you some insights on how Data Accelerator for AI and analytics can help to be able to easily find and use the data a user needs for his analysis without having the knowledge about the underlying storage systems and architectures, and also to get to analytic results faster. I'm not sure how we are doing on Q&A, Gero. Anything open there?
Simon, I think there are two questions open. One is in the chat. The AFM commands were run as root. Can they be run by a regular user?
Yes, we do have special commands that that do the upload. So they do upload, download, and evict. Those can be run with a standard user, not root, but they have limited functionality with the 5.1 release. But it will be extended in the future. So the ones I use exactly are root commands, but we can also provide upload, download, evict functionality with the standard user.
Okay, then there's another question. LFS was running on top of OCP, I assume.
Can you say that again? Sorry.
Oh, LSF was running on top of OCP, I assume.
In our case, we didn't. We installed it in a VM, but also in the Redpaper, it's mentioned that it's possible to run it on top or also in combination with OpenShift. There are plugins that can be installed so that it works together.
Okay, I think that was all.
Okay, thank you, Simon, and thanks to all of our speakers. I think our speakers and panelists would be willing to stay online for a few more minutes. If anyone has any other questions, please feel free to take advantage of this opportunity to ask them. And then I'd also like to remind folks that there's another session on Wednesday, the 18th, another Spectrum Scale user group session, where the topics will be what's new in Spectrum Scale 5.1 And also there will be a panel of experts, so you can ask any IBM Spectrum Scale questions you want, and there will be experts there to answer those for you. So, and as a reminder, we have hosted a number of talks over the past months, and you can view those recordings online. There's a URL for that. Like I mentioned, November 18th, the next session of the user group at SC20 will be taking place. Yeah, so thank you again for joining us.